Okay, so I'd like to pick up where we left off in our last lecture. And last time we had looked at relativistic acceleration. Um, I'd like to try some examples and also extend a little bit um, to get through some of our uh, uh, last little bits of special relativity. So if you'll allow me, oops, I'd like to pick on a few particles, the proton, the neutron, the electron. I'm going to describe the rest mass, which we discussed in our last lecture, in a set of units that is probably a little odd to you, MEV over c squared. You'll see where this comes from about halfway through this lecture. So the mass of the proton is about 938.28 MeV over c squared, mega electron volts per c squared. The mass of the neutron is ever so slightly more, but it's very similar. It's about 939.57 MeV over c squared. And the mass of the electron is considerably smaller. It's about half a mega electron volt per c squared, um, 0.511 uh, MeV over c squared. The Just to put a finer point on this, the the mass of the neutron is about 1,838.7 times as massive as the mass of the electron, and the mass of the proton is about 1,836.2 times as massive as the mass of the electron. Okay, so uh, now that we've added that bit of information to our toolbox, let's try some stuff. So let's look at an electron that is in a head-on collision with a neutron that is moving at 0.6 c. So I'm telling you that the speed of the neutron is 0.6, 60% the speed of light. We'd like to know what was the electron's initial speed uh, if both, wow, that's horrible, both are observed at rest after the collision. Um, so both the neutron and the electron will be at rest in your observation frame after this collision, and you observed that before the collision, the neutron had a speed of 0.6 c. So again, this is just a conservation of momentum problem, and the total momentum before should equal the total momentum after. And so in your frame, the total momentum after was 0. That means that the total momentum before should also be 0. What that tells us is that before the collision, the magnitude of the momentum of the neutron is equal to the magnitude of the momentum of the electron. And so yesterday we had our uh, uh, relativistic uh, momentum discussion where we said that the relativistic momentum is just equal to gamma sub u times m times u, and that's all this is, right? So this is the relativistic momentum of the neutron, this is the relativistic momentum of the electron. Plugging in the mass values, well, note that mn divided by me is going to be 1838.7, right? So all I did here is I took mn and I divided by me, and then I plugged in the speed of the neutron, 0.6 c, and so 0.6 c divided by c is 0.6. I squared both sides, right? So did the same for the electron. Hopefully that's okay. You can pause it here and convince yourself that you can go from here to here. Now we can cross multiply and get that 1 minus the speed of the electron over c uh, quantity squared is equal to, well, if you multiply across, you'll get 5.26 times 10 to the minus 7 UE over c quantity squared. Hopefully, I hopefully that's not too terrible. And so you can kind of combine like terms, and you get that 1 is equal to uh, UE over c quantity squared times quantity 1 plus 5.26 times 10 to the minus 7. You can uh, use this to solve for UE, and what you get is that UE is equal to c times quantity 1 plus 5.26 times 10 to the minus 7 raised to the minus half. And here we can use the statement that uh, that 1 plus x quantity to the minus half is roughly equal to 1 minus x over 2. Hopefully that's not terrible. Let me I can write that out. That 1 plus x to the minus half is roughly 1 minus x over 2 if x is small. So uh, this gives us the following statement, that the speed of the electron before the collision was the speed of light times quantity 1 minus 2.63 times 10 to the minus 7. Note that that is practically, uh, that is very, very, very close to c, but as it must needs be, it's less than c. Now, what would we have expected classically? Well, classically, again, we would have still said that the momentum magnitudes before and after uh, uh, were equal, and that meant that the momentum before the magnitude of the momentum of the neutron had to be equal to the magnitude of the momentum of the electron, just directed in opposite directions. So classically, we have that the momentum is just m times u, and so if you do that, um, you get again this mass ratio of the neutron to the electron, um, and multiply that by the speed of the neutron, 0.6c, you would get that the speed of the electron is 1,103 times the speed of light, which, as we've come to see, isn't feasible. The electron can't travel faster than the speed of light. Okay, so uh, relativistic energy. So in our approach at this, we're ignoring any potential energies, um, and so the kinetic energy is just the total work done from rest up to some speed u. Um, so the integral from 0 to s of f ds is equal to, well, um, we can take the Newton's approach to Newton's second law, that f is dp dt. There's p, so dp dt is just d dt of gamma u mu, and then times ds, because there's a ds out here, right? We treat the mass as invariant in our approach, and so the mass can come out of the integral. and we get from 0 to t of d dt gamma u times u dt is m naught times u times d of gamma u from 0 to gamma u. We can take this apart, right? We can look at the total derivative here and say that m from 0 to u of, or m times the integral from 0 to u of u squared d gamma u plus gamma u du, that is ugly. You are welcome to try and work through that, but let's take a different approach um, to save my voice a little. Um, so another approach that we could take, the OR approach, right, is to say that the kinetic energy is just going to be from x1 to x2 of f dx. I guess I could have stuck with s's, but I didn't. Which is again the same as from x1 to x2, the integral of dp dt dx. Here, we can differentiate p with respect to t, and I would recommend you pause the video, take the derivative with respect to time, and convince yourself that this is what you get. M in the numerator, m times du dt, in the denominator, quantity 1 minus u squared over c squared, end quantity raised to the 3/2. And then, more simply, the x is just u dt. Well, if that's the case, then we can come back up to this, and we can sub in what we mean by dp dt and dx. And so we can say that kinetic energy, we're going to switch to uh, to the integral variables on time right now, at least momentarily, to say that the kinetic energy is the integral from 0 to t of, in the numerator, m times du dt times u dt, and dividing that by the denominator, quantity 1 minus u squared over c squared, end quantity to the 3/2. And then kind of uh, multiplying through and canceling stuff, the dt's go away, and we have that is equivalent to, again, treating the mass as invariant, bringing it outside of the integral. M times the integral from now 0 to u, now we're integrating over u. So m times the integral from 0 to u of, in the numerator, u du, in the denominator, quantity 1 minus u squared over c squared, end quantity to the 3/2. Here we're going to take a slight detour, and we're going to say if we let z equal 1 minus u squared over c squared, then dz is just minus 2u over c squared times du. But we could solve this for u du. U du is going to be minus c squared over 2 times dz. So now let's look at this integral with that little bit of information. M integral 0 to u du over quantity 1 minus u squared over c squared, end quantity to the 3/2. We could write this in terms of z and say that this is equal to mc squared over 2 integral from 1 minus u squared over c squared to 1 of dz over z to the 3/2. This is actually an integral that's not terrible, and what we wind up with is mc squared z to the minus half from 1 to 1 minus u squared over c squared. Note that we absorbed a minus sign and flipped the limits of integration. Plugging in our limits of integration, we get that this integral is equal to mc squared over quantity 1 minus u squared over c squared and quantity square rooted uh, minus mc squared. But going all the way back up here, note that that integral was equal to the kinetic energy. The kinetic energy is just equal to the work done in bringing it from 0 to u. So the kinetic energy is mc squared over the square root of 1 minus u squared over c squared and quantity minus mc squared. Note that that is gamma sub u times mc squared minus mc squared, which is also equivalent to quantity gamma minus 1 and quantity mc squared. So hopefully you followed that. This is going to be very, very, very useful to us. But again, much like we've been doing, we had an equation for kinetic energy that worked fine for us for hundreds of years, worked fine for us through the first 2 semesters of our physics class too. So what happens if U over C is really tiny? Well, again, we can use that statement that we used above. I wrote it somewhere up here, right? That quantity 1 minus b squared to the minus half is roughly 1 plus half b squared. Um, and so gamma u is 1 minus u squared over c squared, all raised to the minus half. That should roughly be equal to 1 plus half u squared over c squared. And so the kinetic energy, which is gamma minus 1 mc squared, will roughly be quantity 1 plus half u squared over c squared and quantity minus 1, all of that times mc squared. And so the 1 minus 1 goes away, and so what we have is half u squared over c squared times mc squared is just half mu squared, which is the traditional kinetic energy equation that you have grown to know and love. I'm going to introduce another quantity, which we're going to call rest energy. It is going to be mc squared. So the total energy, again, this ignores potential, right? The total energy is just the kinetic energy plus the rest energy. And so the kinetic energy was gamma minus 1 mc squared. If I add mc squared to that, what we get is that the total energy is just gamma mc squared. Hooray! Which is just to be mc squared over the square root of 1 minus u squared over c squared. I can't emphasize this enough that this is cool, right? Mass is a form of energy. That is one of our takeaways from this. Let's play a little game here. So we have that the total energy is gamma mc squared, and so we could say E squared is going to be m squared c to the 4 over 1 minus u squared over c squared. We have that the momentum p is gamma mu, and so c squared p squared could be written as m squared u squared c squared over 1 minus u squared over c squared. The fun thing happens here. Note that we could now take e squared minus c squared p. Oh wait, that's got to be fixed. Bad work. We could take e squared minus uh, c squared p squared and say that it is equal to uh, m squared c squared times c squared minus u squared, all of that over the denominator 1 minus u squared over c squared. So we could factor out a c, wow, we could factor out a c squared from this, bring it out front, and now we have m squared c to the 4 multiplied by 1 minus u squared over c squared divided by 1 minus u squared over c squared. And note that this is just equal to 1, right? And so what we have is that e squared minus p squared c squared is equal to quantity mc squared squared. This is just a mnemonic device, just meant to help you remember this. By the way, this is a very useful equation, and we'll see that momentarily. But this is just a mnemonic device to help you remember, um, since I think for a fair fraction of your lives you have remembered that a squared plus b squared is equal to c squared. Well, this equation can be remembered as uh, something like a squared plus b squared is c squared, where you have the rest energy squared plus uh, the momentum times c squared is equal to the energy squared. And one of the reasons that this is so useful is that e squared minus pc quantity squared is an invariant. That means that in my frame, I I will see that that is true, and in your frame, you will see that that is true. Another cool thing that is going to come out of this that we're going to spend some time on is that a photon has mass of 0. Photon is a particle of light. So since the mass of the photon is 0, um, what we wind up with is that E is equal to PC. The crazy thing here is that the photon doesn't have mass, but it does have momentum. And so let's make sure that we put a pin in this and come back to it, because that probably seems odd to you. But the photon does not have mass, but it does indeed have momentum. Okay, so I said that we'd come back to this. I led off with this and said we'd come back to it. I'm going to define an electron volt to be uh, the charge of an electron uh, multiplied by a potential difference of 1 volt. And so 1.602 times 10 to the minus 19 joules is equivalent to 1 electron volt. And so the mass of the electron is 9.11 times 10 to the minus 31 kilograms. So mc squared, the rest energy of the electron, is 8.2 times 10 to the minus 14 joules, right? C is 3 times 10 to the 8 meters per second, so 9 times 10 to the 16 meters squared per second squared times 9.11 times 10 to the minus 31 kilograms is about 8.2 times 10 to the minus 14 joules. We could convert this into electron volts, but the unit that we run across much more often is the mega electron volt. So, so the mass of the electron, or sorry, the rest energy of the electron is 0.511 mega electron volts. The mass of the electron then is just going to be 0.511 mega electron volts over c squared. And so hopefully you can see where this came from, right, in units of MeV over c squared. Okay, so let's do some more examples. Um, a cathode ray tube is becoming much, much less common um, in our modern world, but uh, it's not uncommon uh, for the speed of an electron in a cathode ray tube, like one of those old TV sets or computer monitors, um, to be about a quarter of the speed of light. And so the total energy of that electron is going to be uh, the the rest uh, energy over uh, uh, the square root of 1 minus u squared over c squared. Um, and and so if you carry this out, you get that the total energy of that electron is 0.528 mega electron volts. We could determine its kinetic energy because the kinetic energy is going to be the total energy minus mc squared. So the total energy is 0.528 mega electron volts minus the rest energy. The kinetic energy is then 0.017 mega electron volts. It's a quick way of getting to that solution. One of the reasons why those equations are so useful. Um, if the total energy for a proton is 3 times its rest energy, can we figure out its speed? Well, yes, we can. Um, if the total energy is 3 times the rest energy, well, 3 times the rest energy would be 3mc squared, and the total energy formula is mc squared over the square root of 1 minus u squared over c squared. So we could divide both sides by mc squared, and we get that 3 is equal to 1 over the square root of 1 minus u squared over c squared. Cross multiply, and then square, and we get that 1 minus u squared over c squared is equal to 1/9. And so you can do this algebra problem, but you get that u is about 2.83 times 10 to the 8 meters per second. So again, very, very close to the speed of light. What's its kinetic energy? Well, the kinetic energy, again, is the total energy minus mc squared. And so we said that the total energy here is 3 times the rest energy. 3 times the rest energy minus 1 rest energy is just 2 rest energies, right? 2mc squared. But we know what the rest energy of the proton is, right? The rest energy of the proton is close to 940 mega electron volts per c squared. Or sorry, the rest energy is 940-ish MeV. The rest mass is close to 940 MeV over c squared. So um, so doubling that, the kinetic energy is about 1880 MeV. What if we wanted to know the momentum? Well, again, we have this invariant equation that E squared is P squared C squared plus MC squared. Um, and so E, we already said, is 3 times the rest energy, so it's 3mc squared. So 3mc squared is 9 m squared c to the 4. 9 m squared c to the 4 minus 1 m squared c to the 4 is 8 m squared c to the 4, and that needs to equal p squared c squared. And so you could divide by c squared, and you have that 8 m squared c squared is equal to p squared. So p is going to be root 8 I I m I mc squared over c. Hopefully that is not hopefully in all of those c's I didn't drop a c somewhere, but um, the momentum is root 8 times mc squared over c. But we know what mc squared is, right? Again, it's close to 940, it's 938 and change. I MEV. And so if I take that and I multiply by root 8, I get 2650 MeV and then divided by C. So, oops, try it for yourself. Um, let's do one last little piece. I was trying to keep this to under 30 minutes and I failed. I apologize. But a very, very common example of Einstein's relativity uh, is our radioactive decay problems. And so here we have the isotope polonium-216. It will decay to lead-212 plus an alpha particle, which is just the nucleus of a helium atom. The mass of a polonium-216 in terms of uh, AMUs is two. So be careful. This U is not a speed. It's an atomic mass unit, AMU. Uh, the the mass, the rest mass of polonium-216 uh, is 216.001905 atomic mass units. The mass of the rest mass of a lead-212 is 211.991888 atomic mass units, and the atomic mass unit, the rest mass of a helium nucleus is 4.002603 atomic mass units. If I add these two together, right, so the polonium-216 decays in, we call this the parent, we call this the daughter. Um, the polonium-216 decays into a lead-212 uh, plus a helium nucleus. Um, so if I add the rest masses of the lead-212 and the helium-4, we get 215.994491 atomic mass units. Notice that this the rest masses of the things that this decayed into is actually less than the rest mass that we started with. And so I don't really like calling this delta M, but it's the symbol that your book uses, and it's a very common symbol. Um, it's often referred to as a mass defect, um, and it's equivalent to 0.007414 atomic mass units, which you could multiply by the the equivalent uh, in kilograms to find that the mass defect is 1.23 times 10 to the minus 29 kilograms. If we want to look at the energy, uh, the rest energy that's missing, it's delta mc squared. It is 1.11 times 10 to the minus 12 joules, which is about 6.92 mega electron volts. So where did that rest energy go? Well, since we believe in conservation of energy, it went into the kinetic energy of uh, of the two decay particles of the lead-212 and the alpha particle. So they are now carrying uh, this much kinetic energy. If I if we knew that in our frame uh, the polonium-216 was at rest before it decayed, then we could also conserve momentum, right? We could think of this as a purely elastic collision in some ways, where we now know what the total kinetic energy of these two particles is, and we know uh, that the total momentum has to add up to 0. And so you could figure out what the 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 velocities of the lead-212 and the helium-4 are after the decay. And one of your upcoming worksheet problems will ask you to do something very much like that. All right, I will pause here. As always, you guys are awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your weekend, but not so much that I don't see you on Monday.